All right, Math 5500. The topic we're going to explore in this video is called Anova for regression. So up to now, we've had two methods. We're getting ready to create a third one for testing the statistical significance of a linear relationship between two quantitative variables, x and y. The first one that we've looked at is correlation. I haven't done a lot with correlation. I think there was a video back in lesson 1. We're going to build on that in this lesson from an inference perspective. Not in this video, but in this lesson. The second thing we've looked at maybe ad nauseum is regression. I think we've clearly built the model and we've seen how we can use it. And the third thing we're going to do today, of course, is Anova. This is an acronym for analysis of variance. So for Anova for regression, we examine three sources of variation. We examine what we call a total variation, which is the difference between the observed y's and the mean. We look at an error variation, which is the difference between the observed and the predicted. And then we look at what we call a regression, which is the predicted minus the mean. Now, I think to really motivate this idea, it helps to look at a graph that's kind of conveniently presented. So let's say that we have a regression model. And let's say that we have a y bar, so we have a mean. And let's just choose this for some x sub I, and let's say that we have an observed y sub I right here. So for this x sub I, we have a predicted value, and we have, of course, the mean. So you can think about these as 3 points, x sub I, comma, y bar, x sub I, comma, y sub hat I, and x sub r, comma, y. Again, don't lose sight, this is the observed value. Now, if we look at the variation of these points, just focusing for now just on one x sub I, well, this difference right here is what we refer to as the sum of squares total. So the sum of squares total is going to be the y sub I, so the difference between the observed value and the mean. But we're going to have multiple values of our independent variable. So we're going to want to sum across all of our x sub i's. And of course, we want to square this. All right. Next thing I want to look at is this piece right here. This piece right here is the observed minus the predicted. Well, we should know by now that that's the sum of squares error because, I covered that in a previous video. We should have that one tattooed to the brain. The other deviation is called the sum of squares for regression, or the sum of squares for the model. And that's this piece right here. So this is the sum from I equal 1 to n of our predicted values minus the mean. So as you can tell from this illustration graphically, the sum of squares total is equal to the sum of squares regression plus the sum of squares error. Now, what this does for us is this gives us an indication of explained variation. This component right here gives us an idea of the unexplained variation. In a regression model, what we do is we seek to explain variation. For example, if I'm trying to predict whatever, if I'm trying to predict the value of a stock, what it's going to be on a particular day, well, that stock varies, right? and I'm going to choose predictors that I'm going to use to make the prediction. Well, some of the variation in stock price, it's going to be 22.60 one day, 23. There's natural variation there, right? Some of the variation is explained by the predictors that I've chosen. Some of it is unexplained. That's the error in our model. So we want to examine these two, and the comparison of the two, the ratio of the two, actually turns out to play a role later on. Now let me grab another sheet of paper here. Let's jump into just a brief proof. I'm going to leave a little bit of this to the imagination, and I'll point out the parts that we'll start out with the sum of squares total. And this is the part that I'm going to leave a little vague because it's probably going to be something you'll see again. I know that I can rewrite this as the predicted value minus the mean plus the observed value minus the predicted value quantity squared. Now, you need to convince yourself of that. It took me a while. Well, not a while, but I had to step back and think about it just a little bit. Next thing I want to do is, just FOIL. Easy stuff. So sum from I equal 1 to n. So we're going to have first term. I'm always so afraid I'm going to make kind of a typo, and have to start a video over. And then when I FOIL, so to speak, I get 2 times y hat minus y bar times y sub I minus our predicted. Hopefully I didn't write anything. Let me pump the brakes a little bit, make sure I didn't write anything wrong. All right, next thing I want to do is just distribute the summation through. Nothing fancy here. Sometimes I get in a hurry here and my summations turn out to be just super ugly. And then plus 2 summation I equal 1 to n of wait a minute, I messed up. I'm like, why am I squaring that? That wouldn't be squared. I squared it here. So that takes care of that operation. So y sub hat minus y bar, y minus the predicted. All right. Have no idea what happened there. Not enough coffee, I guess. Now, if you notice this sum of squares total, this is precisely the sum of squares regression, and this is precisely the sum of squares error. So really what I need to be able to show is I need to be able to show that this term is actually equal to 0. Now, what I'm going to do is rewrite this. So I'm going to have, and again, I'm just focusing on this right here. So I have 2 times the sum from I equal 1 to n, and I'm going to rewrite as the first term y hat sub I times the quantity minus y hat sub I. So then I'm going to focus on the net, so I need a negative. Summation, again, y bar times y sub I minus y hat sub I. Again, I'm always afraid I'm going to... These things start to look alike when you're trying to write fast. Now, what happens next is kind of cool in a sense. We saw in a previous video, I believe it was back in lesson 2, that if we take... Well, my cat just decided to make an entrance into the video, so way to go, Cleo. And he's wanting to come back. All right, dude, you gotta move. Come on. All right. So, little cat drama there. If we see that this is actually equal to 0, because we saw in a previous video that that the predicted times the errors will be equal to 0. So nicely, this all becomes 0. And we know that we could rewrite this as negative 2. Y bar is just a constant, so I can pull it out. That's nice. And I just have this. Well, if you notice, this is kind of an old buddy of ours, right? And we know that the sum of the errors is equal to 0. So 0 times any constant is 0. So everybody loves to put this at the end of a proof, so I will too. All right. So you know, that's where we are with the sum of squares total, the sum of squares regression, the sum of squares error, and a proof. All right. Stop the video and more stuff later.